Okay, so we're going to do this example of one-dimensional gradient descent. So we're going to use the forward difference scheme to estimate the gradient, and we're going to do this for the function f of x equals 2x, x squared minus 2x plus 3. Okay, so first, let's just code the function. It has to return x squared minus 2x plus 3. Okay, and we need to import some libraries. So NumPy is basically a library to manage matrix manipulation, and Matplotlib does some graph plotting. Okay, so let's visualize the function. So let's create some x values, and you can do this using numpy.linspace, which is linear space. You specify a start point, an end point, and the total number of steps. fx, y equals fx, and you just need to do plt.plot x against y, and then you show the graph, and you run this. Okay, so you can see the graph here. It's basically x squared minus 2x plus 3. So if you differentiate this function, you get 2x minus 2, and when you set it equals to 0, you get x equals 1, which is the minimum point, as you can see here. So we're not going to use differentiation to estimate the grade to find the gradient at every point, because we are going to anticipate the fact that our functions might be a lot more complicated than what we have here. So we're going to use the forward difference scheme for this, for finding the gradient. So anyway, let's delete this. So let's start by specifying the constants that we need to use. So delta x is basically the value you want to perturb the system to find the gradient. So it's usually set at a small value. Let's just set this. We have the learning rate, which is also usually small. We can set a threshold, and the starting point x equals 6, which can be anything, but let's just set x equals 6 first. So now we are going to code the algorithm, which is iterative. So let's do a while loop, while true. So when you specify this condition, while true, it means it will keep running until the terminating condition is met, and we can specify that later. So now we want to calculate the gradient, the approximate gradient, using the forward difference scheme. So what we remember, the function is basically just f of x plus delta x. This is your small perturbation. Delta x is your 1e minus 8, which is small. You take this value minus f of x, and you divide the entire thing by delta x. So what this does is it approximates the gradient at f of x by using this forward difference scheme. So now you want to calculate your new x. Your new x will be equal to x minus learning rate multiplied by the gradient, as you recall from the slides. So now the terminating condition is when the new x is about the same as the previous value x. So you can code this by doing if new x minus x divided by x, which is the old value of x. And we can put an absolute here so that there won't be a negative value. So if this percentage change is smaller or equal to the threshold value, you want to break, which means you break out of the loop. So let's make it neater by just specifying this. Okay, so that's done, and after you need to set your value of x to be equal to the new value of x. And let's just print x and see what happens. So let's run. Okay, see, you see the value decreasing. It's approaching 1, which is your minimum point. And it stops when the difference is tiny, smaller or equal to your threshold. And that's it. So this is your answer. So this is your minimum point. So let's visualize this. You can visualize this by, let's just have a new list called xPredict equals a list. And we're just going to attach the new value of x at every time. Okay, I'll stop printing this value. So now what you need to do is to plot the graph. So then we need that linspace thing again, np.linspace. Let's do -10, 10, 100 steps, and let's plot x against f of x. Okay, so now you want to scatter you want to see how the value x changes as we update it from the start value of x equals 6 to the point you reach the minimum. So we can do a plt.scatter. We can do a xPredict f of xPredict marker. It basically just tells you how it looks like. plt.show. Okay, so I don't want to show everything because it will look too messy, but let's just see how it looks like now. Okay, what's happening? So yeah, we need this to be a strange. What's happening? X equals this. plt.plot x fx. F of xPredict. Oh, okay. So xPredict has to be a numpy array. Let me just np.array. You just convert it to a numpy array basically. Okay, it's a small issue. Okay, you can see here, this little crosses is basically taking steps towards the minimum point. Okay, let's make this clearer. Let me set a color. Color equals red. And then to make it clearer, I'm not going to plot all the crosses. I'm going to plot at every time step of 100. So what this does is it picks up values at every 100 point. So we get sparser values and not a whole blob of crosses. There you go. So you can see you start at x equals 6. You take steps all the way to the minimum point. And there you go. That's your one-dimensional gradient descent algorithm.